We start by, for part A, by getting the grading spacing. And the grading spacing LD is given by 1 over the diffraction grading given, which is 600 slits per millimeter, and this tells us that D is 1.67 times 10 to the minus 6 meters. And then we know that D sine theta for a diffraction pattern is a multiple of the wavelength, so it's m lambda, which means that theta equals sine inverse of m lambda over D. And now for m equals 1, we can say that theta V1, or the violet, is going to be the sine inverse of the wavelength for the violet, which is 380 times 10 to the minus 9 meters, over D, which is 1.67 times 10 to the minus 6 meters, and that gives us about 13.2 degrees. And for the red, for m equals 1, we get sine inverse. The wavelength for red is 750 nanometers over D, which is 1.67 times 10 to the negative 6 meters. And that gives us an angle of 26.7 degrees. So the first order visible spectrum appears with deflection of an angle for violet of 13.2 and an angle for red of 26.7. For part B, we have m equals 2. We start with that, and that way we get theta violet 2 is sine inverse of the wavelength at that point is going to be 2 times 380 nanometers over 1.67 10 to the minus 6 meters, and that equals 27.1 degrees. And for red at m equals 2, we get sine inverse 2 times 750 nanometers over 1.67 times 10 to the minus 6 meters, which is 43 degrees. And lastly, for m equals 3, we get theta violet 3. Oops, I made a mistake. If you plug these in for the red at m equals 2, you get 63.9 degrees, not 43. If we do violet at m equals 3, we get minus sine inverse of 3 times 380 nanometers over 1.67 times 10 to the minus 6 meters. Red 3 gives us violet 3 gives us 43 degrees. And then if we do the same for red at m equals 3, we get sine inverse of 3 times 750 nanometers over 1.67 10 to the minus 6 meters, which will give us an undefined value, because we get a sign of bigger than 1, which can't be the case.